Now, in quantum mechanics, again, what we discuss about Hamiltonian, am I right? One-dimensional motion. Again, I better to rub it out. Now I am discussing quantum harmonic oscillator. Let me get into quantum harmonic oscillator. That this potential, whatever the discussion we did on potential, that remains same. Only thing is we can't have continuous energy in case of quantum mechanics. We should solve Schrodinger equation. Then we have to talk about energy, isn't it? Now again, if I write Hamiltonian, that will be p cap square by 2m plus half m omega square x square. Am I right? So can I write like this? And your Schrodinger time independent equation, that is h cap psi is equal to E into psi, isn't it? I can write it as minus h bar square by 2m into d square psi by dx square plus v of x, that is half m omega square x square psi is equal to E into psi. This is differential equation, second order differential equation with variable coefficient. That's not that easy to solve. Is that okay? By some substitution, it can be converted into Hermite differential equation. Hermite differential equation, again with variable coefficient. And we should solve that one by power series. That's quite lengthy method. And what we do is we choose some other method. We call it one as algebraic method. He differentiate method of solving this quantum harmonic oscillator into two parts. One is algebraic method or ladder operator method. Another one is analytic method. Analytic method means solving the differential equation from pure mathematical point of view. I mean by our power series and all. We shall discuss that one, okay? In the later part of differential equation, we shall discuss about that one. Yeah, definitely it is possible to analyze some part of quantum mechanical oscillator analogous to classical spring mass system. We shall see some analogies there. Some analogies there, not all. But again, when you apply the whole situation, you better to apply in a situation where you have oscillator, which is again any oscillation. Remember, any potential, if you take the oscillation amplitude is very small, that is simple harmonic motion only. So he's asking only in case of oscillation which is parabolic potential. That's what we are discussing only in case of this kind of potential. But what I am saying is this type of potential will come for any function if you take what you call displacement from the mean position, which is very small. That's what we have shown using Taylor expansion. So as long as that displacement from the mean position is very small, our potential will show this nature. So thereby we are covering a lot of applications. It need not be completely this kind of curve for all x value. When x is nearly equal to x naught, which is the minimum point, so it will show this nature. Yeah, there are some analogy between classical and quantum oscillator, but not much, okay, because both are different. So in case of classical, energy is equal to continuous. In case of quantum, energy equal to discrete. Again, lot of difference are there. In case of classical, particle cannot go outside classically allowed region, am I right? Classically forbidden particle cannot enter into that region because kinetic energy will be negative. But quantum mechanical, there is a finite probability of finding the particle in the classically forbidden region also. We shall see that one, okay? All of the such situation. Wait a second. He asked v double dash of 0. Am I right? Now suppose if I take this one, if I take purely half kx square, am I right? You should have the idea what is the role of k. This is v of x. Let me take v dash of x. What is v dash of x? K into x. Am I right? So take first derivative and equate that first derivative to 0. What is that one? Kx equal to 0. That means x equal to 0. X equal to 0, which is a point where first derivative equal to 0. So again, that point may be either maxima or minima, isn't it? When you equate first derivative to 0, if you find that point will be either maximum or minimum. Now let me take second derivative, v double dash of x. What is this one? That's equal to k. Am I right? Now again, let me take second derivative at x equal to 0. That's equal to k itself, which is greater than 0. Then x equal to 0 is the point of minimum. Is that okay? So second derivative at 0, that is nothing but k. Second derivative at 0, that will decide how first derivative changes about x equal to 0. That means second derivative at 0, it will decide how much curvature this curve has. If more the curvature, then first derivative changes quickly, your slope changes quickly. Less curvature, isn't it? So take it like this. Again, try to plot that one, okay? So take this kind of curve, take this kind of curve. Here, about this x equal to 0, your slope is varying very slowly. Here, about this x equal to 0, slope is varying very quickly. K will decide that one. K is nothing but second derivative at 0. Whatever spring constant we say, again, in our potential point of view, it will talk about curvature. Any question here? So that's why what I had is, I after Taylor expansion, I got this one, am I right? V double dash of 0, half V double dash of 0 into x square. I put this one as a k. And physical significance of k is, it will decide curvature actually. Try to plot that one. So try to plot half x square, half 10x square, half 100x square. Try to plot this one, you will understand how it varies and what is the role of it. Is that okay? I hope you have gone through maxima minima concept in case of derivative, application of derivative. Okay? Yeah. Now again, our next idea is to solve this equation. Am I right? Minus h bar square by 2m d square psi by dx square plus half m omega square x square of psi is equal to e into psi. Remember this ladder operator method that is used in many other cases also. Am I right? Even in case of field quantization, they use similar method actually. Only thing is some basic physical parameters are different. That's why again it's very better to discuss the full ladder operator method and how to find quantization of energy, ground state, excited states and all. Okay? You don't have to solve the differential equation. You have other method also. We shall just stick into that method. Now, when you see the whole equation, yeah, so quickly, is there any questions? While solving, you will not only get psi of x, you will get e also, remember. Using these two, you can write your psi of x comma t, am I right? That's equal to psi of x into e power minus I et by h bar, isn't it? You don't have to go for time dependent Schrodinger equation. Time independent Schrodinger equation is sufficient. If you solve it, it's over. Again, in case of classical harmonic oscillator, he's saying that we are taking mass spring concept where spring is there to provide restoring force. Okay, so suppose if you take an atom which is sitting in a solid, is that okay? And now it is bound by some metallic bond or some other bonding with the other atom around. So around that atom. So then when you just displace that one, it will try to regain its original position, mean position. Oscillation of atom in a solid, usually it is simple harmonic. Is that okay? Or if you take some other example, suppose if there is a molecule, diatomic molecule, the best example, HCl. H and Cl are bound by some force, am I right? That again, when you change their what you call position, it will try to regain its original position. You can just assume that diatomic molecule as a kind of there is a spring and other molecule. This force constant, everything that depends on nature of the bonding actually. Again, like that. Again, we can model. Again, we should apply the whole story to microscopic domain. We should not think that always we take mass spring concept, but we can apply this one in many applications. Diatomic molecule is the best idea, where we apply this one and we find diatomic molecular spectra in case of IR region, where you will find very exact match between them. Okay, so between our theoretical part and experimental part. That's a good question. Definitely, we will not apply this one to mass spring concept, but forces. I mean, here it is bonding, that bonding between H and Cl, that will act like a spring actually. And again, that will give some restoring force. Not coefficient. What he's saying is, again, what makes that spring, what makes the restoring force in case of quantum harmonic oscillator? It's a bonding. It's some force will play the role actually. Bonding with other atom and all. In case of lattice or in case of free what you call diatomic harmonic oscillator, anywhere. Is that okay? Bonding between those atoms, that will play the role actually. Not getting what are those specific conditions you are talking about. So take HCl molecule or take O2, oxygen molecule, or H2. Again, why those two atoms are together? They are together by some bonding, am I right? And that again, that bonding between them, that bonding will have some, it will act like a spring. That's what we imagine. And we model that one. Or if you take any atom in a solid, isn't it? It will vibrate actually. It will oscillate about its mean position. That will become three-dimensional simple harmonic oscillation. Quite different story. Okay, quite different story. Yeah, you can call it as intermolecular potential energy. You can say like that. Okay, intermolecular potential energy or bonding potential. That will have some minimum. That will have some minimum. So that it will again if you keep it at rest, it will be in a equilibrium position. If you start giving the energy, it will start vibrating. Okay, that's what we see in case of application. Now again, we can do all of these quantum mechanical steps only in case of microscopic domain. That's what I'm saying. Ultimately, we will not apply this one for spring mass system. Whereas in case of spring mass, again, this will give the answer that ground state energy cannot be 0. But in case of spring mass system, you can put mass at rest, am I right? Where its energy go to 0. It will not happen usually. That's why we apply the whole story to any microscopic thing. You can get the result. You can predict most of the part. Yeah, that's correct. Okay, intermolecular potential energy, that's also correct. Okay, or bonding potential or something. Okay, we shall see in molecular spectra. Again, this ladder operator again. Yeah, he said. I think he's asking. I talked about field quantization. Am I right? In case of field quantization, your electric field and magnetic fields are going to play the role. Electric field and magnetic field together will decide total energy actually, or Hamiltonian. There again, it's a quite different story. That's why I'm not discussing that one. But we do apply the similar method. That's why you should know that one. That's why I'm doing it very completely. Along with that, again, there may be some direct question in the mathematics that we do while deriving this one, some commutation relation like that. That's why you should know how to derive it using ladder operator. And in case of fourth chapter, when we come across angular momentum, again we do the similar thing actually, ladder operator. Is that okay? To find eigenvalues and eigenvector of angular momentum operator. Okay, that's why again this have got a lot of application. We need some practice. Now what we do is, again I'm going to imagine this one as h cap into psi is equal to E into psi, where h cap I can write as p cap square by 2m plus half m omega square x square operating on psi is equal to E into psi. Just check it out. Now what I do is I'll take 1 by 2m outside. What will happen is p cap square plus m omega x the whole square. If you take one more denominator m outside, here m square will be there. Divide and multiply by m here. Is that okay? Whole square of psi is equal to E into psi. Can I write like this? No, this is a kind of a square plus b square. Am I right? This whole thing is a kind of a square plus b square. Again, that gives some idea that we can define some operator. We can define some operator so that from those operators we can define these two. So that was the idea. Again, I'm not getting into detail about that idea. I mean, original idea, how they got this ladder operator method and all. Let me quickly start that one. So we define two operators which are not any observables. P cap is observable, x cap is observable. Am I right? It is position, it is momentum. Those are observable quantities. But whatever I am defining, these operators, they are not observable. Later we shall see they are not Hermitian operator also. Okay. Now look at here. I'll take a two operator. One is a plus cap and another one is a minus cap. We call one as rising operator, other one as lowering operator. We shall see again why we call it like this. Okay. Now this a plus cap, it is defined as 1 by root of 2 h bar m omega, 2 h bar m omega minus I into p cap plus m omega x cap. A minus is equal to 1 by root of 2 h bar m omega plus I into p cap plus m omega x cap. We define, look at here, there may be a lot of question here why we take like this. It's a kind of trick, okay, trick to find energy, eigenvalues and all. It's not any ordinary method of solving the differential equation and all. It's a kind of trick. A plus cap and a minus cap. Is that okay? They are not any observables, just like momentum and position. Now next one is you should multiply them. You should multiply a plus into a minus, but while multiplying you should take care. You haven't done this algebra earlier. I mean, if you are a new student, you haven't done this algebra earlier, this kind of algebra, operator algebra. We should be very careful when we do that operator algebra. Now let me multiply this. Look at here. When you have a plus b into c plus d, what you will do, you will just multiply as it is. You don't care whether you write AC or CA. Isn't it? Both are same. But in case of operator, they need not be same. Why? This is an operator. You are going to operate on something. Operating x cap on some function, then operating p cap, that is different from operating p cap first, then operating x cap first on the same function. Both are different. So that's why again when you multiply two operators, look at here, p cap into x cap is not same as x cap into p cap. We should be very careful. Let me show that one. Let me show that one. Now you should take A minus into A plus. Product of A minus cap into A plus cap. Is that okay? When you do that one, 1 by 2 h bar m omega. Now let me write it down. A minus is I p cap plus m omega x multiplied with minus I p cap plus m omega x cap. Just check it out. We should multiply these two. Yeah, operators usually obey matrix multiplication rule. That's a good idea. We shall see that one in case of linear algebra chapter. Okay. Now that is equal to 1 by 2 h bar m omega. We get here I p cap minus I p cap. What is this one? Minus I square p cap square. P cap square. So this one into this one plus m omega x the whole square. Look at here, you got this term actually. You got this term. So now next part is I p cap into m omega x cap. I p cap into m omega x cap. M omega x cap into minus I p cap. It should be in that order only. M omega x cap into minus I p cap. You can't change the order. You should be very careful while doing this multiplication. Is that okay? I p cap into m omega x cap, m omega x cap into p cap. You can't write it ulta. If you write it ulta, they will get cancelled. Am I right? If you write p cap here and if you manipulate other constant, it will become cancelled actually. Is that okay? Suppose it is like this: a cap plus b cap into c cap plus d cap. Suppose you are doing this multiplication. Okay, they are operators. Suppose they are not any numbers. Again, you will understand why do we take this one. Okay, I just commented on that one. It's a kind of trick. Again, where we can find the answer without solving any differential equation. Okay, yeah. Why we call this as a rising and lowering operator, that reason will come just later. Okay. Now again, this multiplication is similar to this one. Am I right? Operator multiplication. Now you should multiply it like this: a cap into c cap plus a cap into d cap plus b cap into c cap plus b cap into d cap. Now you can ask the question. Can I write this one as c cap into a cap? No. Because this whole thing is an operator. It's going to operate on something. You don't know if you reverse the order, what would happen. If you reverse the order of operations, something else may happen. We shall show that one. Again, why it will happen and all. Is that okay? So that's why you should be very careful while writing this one. Or suppose if you have a cap plus b cap the whole square. Now you should not write this one as some a square, a cap square plus b cap square plus 2a cap b cap. This is not equal to this one. You should not do it like ordinary numbers. What you should do? A cap plus b cap into a cap plus b cap. You should do like this. Operator multiplication. Okay. That is equal to a cap into a cap square, a cap into b cap, a cap into b cap, b cap into a cap plus b cap square. These two need not be equal. That's what I'm saying. Is that okay? Those two need not be equal because it's an operator. You are going to operate it on function. And order of operation does matter. If you reverse the order, you may get some different outcome. So that's why while multiplying these two, be careful. That's what I'm saying. I p cap. That is so again I square minus I square into p cap square. Okay. I p cap into m omega x cap. I p cap into m omega x cap. M omega x cap into minus I p cap. M omega x cap into m omega x cap. That is m omega x cap the whole square. Okay. So now what I do is 1 by 2 h bar em omega p cap square plus m omega x cap the whole square. What I do here is I'll take minus I m omega common because those are constant. Remember, m omega I minus 1, those are constant. You can manipulate them anywhere. But order of x cap and p cap, that should be same. In this one, p cap come first, x cap come next. Am I right? In this one, x cap come first, p cap comes next, isn't it? That order does matter. You can manipulate this m omega, you can keep it anywhere. That's why I'll take minus I m omega common. If I take minus I m omega common, what will happen here is p cap, x cap into p cap. I'll get this one, x cap p cap minus p cap x cap. I'll get this one. Just check it out. Yeah, that's a good idea. Wait a second. Is that over? X cap p cap minus p cap x cap. I'm taking minus I m omega common, so that I'll write this part first, then this part. Okay. Now we shall see what is this operator equivalent to. We call it one as commutation. We call this one as commutation between x cap and p cap. This is the symbol for commutation. We call this one as commutation between two operators. Look at here, a cap comma b cap. We call this one as commutator. That is a cap b cap minus b cap a cap. Commutator between a and b. We say like this. And what we write is, we prefer writing a minus cap, a plus cap. That's equal to 1 by 2 h bar m omega. Okay, 1 by 2 h bar m omega. 1 by 2 h bar m omega. P cap square plus m omega x cap the whole square. Now let me just take this this one separately here. When I divide, I think minus I by 2, what will remain? Minus I by 2 h bar minus I by 2 h bar minus I by 2 h bar. I better to put the flower bracket here or some other bracket here. Why? It looks like commutator again. Is that okay? So shall I write like this? That's the best idea. Minus I by 2 h bar. Commutator, again I have taken this one inside. Are you getting my point? I have taken this one inside. Commutator between x cap comma p cap. Can I write the multiplication like this? M omega got cancelled. 2 h bar remained when I take it inside. Is that okay? Just see that one. Now our aim is to find what is this equivalent to. X cap comma p cap. What is this operator? Again, commutator is equivalent to. Okay. Now we shall see that one. How do you find any operator? By operating, isn't it? You will find what it will do, isn't it? Now what I do is I am going to operate this one on some function f of x, some dummy function. Again, I am not taking care what is this function and all. I am trying to find what is its nature. Now that is nothing but, look at here, x cap p cap minus p cap x cap operating on f of x. Am I right? Now x cap p cap f of x minus p cap x cap f of x. Okay. Now this means x cap p cap f of x means you should operate p cap first, then you should operate x cap. P cap x cap f of x means you should operate x cap first, then you should operate p cap. Now can I put these brackets because I feel comfortable with it. Let me put this bracket. Now what is that p cap operator? Again, operating p cap operator first means minus I h bar dou f of x by dou x, isn't it? Minus p cap. What is p cap operator? Minus I h bar dou by dou x again, isn't it? Now wait a second, let me operate p cap later. Operating x cap on f of x is nothing but again just multiplying by x. Operating x cap, because x cap operator is variable x itself. Can I write like this? Now you have to operate p cap on this x into f of x together. Now see the step very carefully. You should do all of this yourself again, because very important part, because you do some part of linear algebra here. Now x cap comma p cap operating on f of x, that's equal to minus I h bar. I can manipulate this minus I h bar anywhere. Okay, I can take it outside. X cap into dou f by dou x, that is first part, isn't it? Now second part, minus p cap minus plus I h bar. Am I right? Because p cap is minus I h bar, one more negative sign will come. Dou by dou x of x into f of x. Can I take like this? X into f. Okay. Now let me do differentiation here. Minus I h bar x cap into dou f by dou x plus I h bar. Take differentiation. What is this one? X into dou f by dou x plus f into f. Am I right? F into 1. Now what will happen here is x cap comma p cap f of x, that's equal to minus I h bar x cap dou f by dou x plus I h bar x cap dou f by dou x. X cap you can write as x, you don't have to worry. You can write as simply x, suppose if you are worried about that one. Okay. These two get cancelled. What remain? I h bar into f of x. That means operating this one on any function. Look at here, we haven't talked about what is the nature of this function. Operating this one on any function or any state, we say state in quantum mechanics, that's nothing but multiplying it by I h bar and doing nothing with the function. You haven't done any derivative or something, isn't it? That's why we represent x cap comma p cap, that's equal to I h bar into identity operator. You should write identity operator actually. Identity operator means it does nothing. If you operate identity operator on something, it does nothing actually. We define identity operator like that. Actually, we should write identity operator. Operating this one is nothing but operating I h bar into identity operator. That means you should do nothing, but you should multiply by I h bar. But what we write, we simply write it like this. We simply write it like this. But that's in a linear algebra sense, it is little wrong. Why? How multiplication of two operator can be scalar? It's a scalar. I is a scalar, h bar is a scalar. Am I right? It should be a kind of operator, isn't it? That's identity operator, but we will not write that one actually. Okay? Yeah. So that's why in place of x cap and p cap, we can write I h bar. Once you substitute that I h bar, a minus a plus cap. This is very basic commutation relation. Okay, I just proved that one. That's very basic commutation relation. You will understand. Look at here, 1 by 2m p cap square plus m omega x the whole square. What is that one? Any idea? That's your Hamiltonian. Just check it out. I can write as 1 by h bar omega. Take h bar omega outside. 1 by 2m p cap square plus m omega x the whole square. You can write as Hamiltonian. And now I'm going to substitute here x cap p cap, that's equal to I h bar. H bar will get cancelled, plus half it will remain. Just check it out. Okay, when you substitute this one back, minus I square will happen, minus I plus I, minus of I square, that's equal to plus 1. One more h bar will come, it will get cancelled. Actually, there should be some identity operator here, but we will not write that one usually. Okay. If operator operates on constant, again, if it is derivative operator, you will get 0. If it is x cap operator, it's just multiplying by x cap. Okay, it's all operator property, not on something which you are operating on. I mean, he may be thinking that what if this is operating on a constant? I h bar into that constant. You don't have to worry. Again, that's a kind of identity operator. Okay, identity operator multiplied with I h bar. Now, in this one, I'm going to solve it for h cap. H cap is equal to h bar omega into a minus cap, a plus cap minus half into h bar omega. Is that okay? So can I write like this? Now similarly, if you find a plus cap into a minus cap, okay, a plus cap into a minus cap, what you will get is, I think, 1 by 2 h bar m omega. Again, the similar part, but here you will get ulta. Here you will get ulta. Just do this one. So do it yourself. Practice that one. I have done a plus into a minus. You do a plus, sorry, I have done a minus into a plus. You do a plus into a minus. Okay. When you do a plus into a minus, again, what you will get is, you will get similar part, but one more negative sign. Minus half. Here you had plus half. Here you will get one more negative sign. Just check it out. 1 by h bar omega h cap minus half. So that using that equation, if you try to define h cap, that's equal to h bar omega a plus cap a minus cap plus half. You got two way of writing Hamiltonian operator. Let me keep it here, one side. Okay. H cap can be written in two ways. One is h bar omega into this one, a minus cap, a plus cap minus half. Another way is h bar omega into a plus cap, a minus cap minus half. Just check it out. Sorry, plus half or minus half? Plus half. There are two ways of writing the same operator. Now, one more thing that you need to work out, that is needed for exam also, that is commutator between a plus cap and a minus cap. Or wait a second, he is taking ulta. Commutator between a minus cap and a plus cap. What do you mean by that? A minus cap, a plus cap minus a plus cap, a minus cap. Isn't it? That's also needed. That's also needed. A minus cap. So can you just do that one? I have given a plus into a minus. This one. I have given a minus into a plus. First one. Just subtract them. What will you get? Just so check it out. You will get that is equal to 1. You have minus half here, you had plus half here, they will get added. One more negative sign in the middle. Okay, you will get plus 1 here. Just try to do that one. So next parts are very important here. You should remember that a plus cap and a minus cap. You should by heart them because that is needed for problem solving. Okay, yeah. Just go through this one. Let me come online it again 7:30. Okay. Any question quickly? I mean, are you asking we can't solve this problem just by 1D box? We can't solve it like 1D box because 1D box differential equation was very easily solvable. Differential equation. It had no variable coefficient, but this differential equation had variable coefficient. Okay, differential equation method of solution, that's quite difficult here. We shall see. Okay, again, what does that ladder operator signifies, why we call that one as ladder operator in the next session. Okay. Okay. I mean, how did the intuition of this ladder operator method comes, isn't it? It's not an ordinary method, am I right? We define something strange initially and then we proceed. Differential equation solution, you have some path. You have differential equation, again you have some mathematical method and you are solving that one, isn't it? That Hermite differential equation, those methods were exist actually. So again in the last century also. In the engineering part, they used to apply those things. So power series method and all. But how did this ladder operator method, that inspiration comes? I think I too have to work on that one. Okay, history. Observe this further step very carefully. Okay, I mean in this one you will have many properties of this ladder operator also. Now what I do is I'll take some state. Okay, I'll take suppose I'll just take one of this Hamiltonian and I'm going to apply it on wave function. What should I get? H cap into psi. I should get E into psi. Am I right? E is energy. Now I can just substitute any one of this actually. I can write h bar omega into a minus cap. Can you hear me? Any problem? Operating on psi is equal to E into psi. Or I can write h bar omega a plus cap a minus cap plus half psi is equal to E into psi. Now I'll put one statement here. Again, he put that statement in a box. You can just see the book. If psi satisfies Schrodinger equation with energy, okay, if psi satisfies Schrodinger equation with energy E, again we should have a statement first, then we shall try to prove that statement. Again, this is a kind of Schrodinger equation. If psi satisfies Schrodinger equation with energy E, then, I mean, so what do you mean by that one? H cap into psi is equal to E into psi. If psi satisfies Schrodinger equation with energy E means, if you operate H cap and psi, you should get E into psi. We call E as energy, isn't it? Then a plus cap operating on psi. Look at here, psi is some function. When you operate a plus cap on that one, what you will get? You will get some other function. A plus cap into psi, that is different from psi. Okay. Then a plus cap into psi satisfies Schrodinger equation. Satisfies Schrodinger equation with energy E plus h bar omega. E plus h bar omega. I mean, a plus cap into psi is such a state, it is such a wave function. When you operate h cap on this one, what you will get is, you will get E plus h bar omega into the same state. Remember, a plus into psi satisfies Schrodinger equation, means it will follow kind of eigenvalue equation. Schrodinger equation, we call that one as eigenvalue equation, am I right? It will follow a kind of eigenvalue equation. I mean, if you operate h cap on that one, you will get a constant into the same state. That constant is E plus h bar omega. So that is the idea. So this is the statement. We shall try to prove that one. Is the statement is clear? If psi is the solution of, again, or mathematically I can write like this. If h cap psi is equal to E into psi, if psi is the solution of Schrodinger equation with energy E, then h cap a plus cap into psi. A plus cap is some other wave function which is a solution of Schrodinger equation with energy E plus h bar omega into a plus cap into psi. Okay, I'm running out of space here. Then h cap into a plus cap psi, that's equal to E plus h bar omega, a plus cap into psi. This is eigenvalue equation, operator, function. A plus cap into psi, I have taken this together as a function. Is that okay? Operator, function, eigenvalue is E plus h bar omega. So now read the statement. If psi satisfies Schrodinger equation with energy E, then a plus psi satisfies Schrodinger equation with energy E plus h bar omega. Is that okay? We should prove that one. Let me start with this one. H cap, again, so this is given. What is given? H cap into psi is equal to E into psi. Okay. Now let me take h cap into a plus psi, a plus cap into psi. Is that okay? Let me take this function. Now h cap, I can use any of these two. Isn't it? I kept this one. This was very useful. Okay. I kept this one. I can use any of those two. Isn't it? Let me use the second one. In place of, again, that's equal to, look at here. So this is equal to, what is h cap? H bar omega, speak out, a plus cap, a minus cap, plus half into a plus cap into psi. Just check it out. Now what I do here is I am going to do some manipulation here. But before doing manipulation, I'll take this a plus cap inside. So now look at here. A plus cap is right side, isn't it? We can multiply it from right side actually. Again, in case of operator algebra, you should do like this. Again, after some practice, you may get much more idea. So again, you can't keep that a plus cap here. Again, look at here. This is one operator. This whole thing is one operator. This is another operator. It should be in that order only. This should be first. This should be next. Now you can shoot in this a plus cap from this side, but you can't keep this a plus cap here, and you can't multiply in this side. It should be in that order. What we can do here is h bar omega, because operator will follow that kind of algebra. If I take this a plus cap inside, a plus cap, a minus cap, from this side, that is a plus cap, plus half a plus cap into psi. Can I write like this? It is nothing but, again, this operator is multiplied with this operator. When you multiply this operator with this operator, you should write a plus a minus into a plus, half into a plus. It should be in that order. Now what I do is, again, I am using operator algebra only. I can take that a plus outside from this side. Look at here, a plus is here, left side, a plus is here, left and right both are same. Only one factor, only one operator. Okay, I can take that a plus outside from this side, h bar omega, a plus cap. If I take it outside, what will happen? A minus cap A plus cap plus half into psi. Just check it out. Now again, if you are worried about this step, just multiply A plus from this side and you will get this step actually. Now A minus A plus, it is there here, along with minus half, you will get H cap, isn't it? Then what I do here is H bar omega, A plus cap, A minus A plus, A minus cap, A plus cap, minus half, plus 1. Can I write like this? Just check it out. Minus half plus 1. Minus half plus 1 is plus half. Okay. So that this whole thing together with H bar omega you can keep it anywhere. It's a scalar. It is not an operator. You can keep it inside or outside. It doesn't matter. What I can write here is A plus cap. A plus cap. I'll keep it outside. H bar omega. A minus cap. A plus cap minus half. Okay. Minus half. Again, this again. H bar omega into this part plus 1 plus H bar omega. 1 means you have taken H bar omega inside plus H bar omega. Okay. Let me put them in a bracket operating on psi. Just check it out. Is that okay? So do it again. Okay. Later do it again. So now what I do here is, what is this one? This is my Hamiltonian. So now the result is A plus cap Hamiltonian plus H bar omega operating on psi. Is that okay? Plus H bar omega operating on psi. That is equal to A plus cap H cap psi plus H bar omega psi. Somewhere I'm missing something. Yeah, that's correct. That's correct. Okay. Now, what is H cap psi? We have started with this one. What is H cap into psi? Psi is the solution with the energy E. That's equal to E into psi. E psi plus H bar omega psi. So that this is equal to A plus cap E plus H bar omega psi. E is scalar. H bar omega is scalar. Isn't it? I can write this one as E plus H bar omega into A plus cap psi. What I have proved here is, I proved that statement. That's equal to E plus H bar omega. This is scalar. You can take it outside. Okay, this is not any function. You can't manipulate function. You should keep the function as is. That is psi. You should operate A plus. Okay. You can interchange these two positions into A plus cap psi. That's why we call that one as a rising operator. Is that okay? Why? If you operate A plus on psi, you will get such a state, you will get such a wave function whose energy is H bar omega higher than this one. That's why we call that one as rising operator. It will rise the state. Is that clear? Quickly. Any question? So similarly, we can make one more statement. We can make one more. I'll not write it as a statement. I'll write mathematically. Okay. If you operate A minus cap on psi, it is such a state that it is a solution of Schrodinger equation with energy E minus H bar omega. If you operate A plus on psi, it is such a wave function. It is such a wave function that it follows Schrodinger equation with energy E plus H bar omega. If you operate A minus on psi, it is such a wave function that it satisfies Schrodinger equation H psi equal to E into psi. It satisfies Schrodinger equation with energy E minus H bar omega. If psi satisfies Schrodinger equation, so can I write like this? If then first one, second one, these two will happen. If psi satisfies Schrodinger equation with energy E, then A plus psi satisfies Schrodinger equation, eigenvalue equation with energy E plus h bar omega. A minus psi satisfies Schrodinger equation with energy E minus h bar omega. Is that okay? And we can continue this argument. Look at here. A plus cap operating twice on psi. A plus cap operating twice on psi. It is such a state that it will satisfy Schrodinger equation with energy E plus 2h bar omega. E plus 2h bar omega. So similarly, A minus square psi operating on h cap, it is such a state, it is such a wave function that it will satisfy Schrodinger equation with energy E minus 2h bar omega. A minus cap square psi. It is such a state that operator state eigenvalue state with eigenvalue E minus 2h bar omega. Now we can make a ladder here with corresponding state and energy actually. I think you can see the book where a cat is climbing the ladder, isn't it? I think that is Schrodinger cat. Now look at here, I can have a ladder here. I can have a ladder here. If suppose this is state psi with energy E, can I say like this? If that is a solution of Schrodinger equation with energy E, we say that is the state with energy E, stationary state. Am I right? Now, A minus cap psi, that is the state with energy E minus h bar omega. A minus cap square psi, that is the energy with E minus 2h bar omega. A plus cap psi, that is the state with energy E plus h bar omega. Like that you can write. Is that okay? Here again, if you keep on applying a rising operator, you will get a state with energy which is h bar omega greater than the earlier one. Isn't it? So that's why we call that one as A plus cap as rising operator, A minus cap as lowering operator. If you keep on operating that one, you will get those kind of state. Now look at here. How long you can operate A plus cap? You can operate any number of time. But how long you can operate A minus cap? Look at here. E minus h bar omega. E minus 2h bar omega. So when you continue like this, you may get negative energy. Negative energy is not possible. Why? What is our potential? Half kx square. What is the minimum value of the potential? What is the minimum value of the potential? 0. Energy should exceed minimum value of the potential. Energy should be greater than 0. Is that okay? Energy cannot be 0 here. So that's why, look at here, how long you can apply this lowering operator here? You can't apply any number of time. So maybe if you start applying, again, if you keep on applying that one, you may get into the situation where E minus some n h bar omega, you may get into negative value because you are subtracting, isn't it? You have one value, arbitrary value here, you are keep on subtracting this one with a value h bar omega to h bar omega, this subtraction term is increasing, am I right? Then you may get into the situation of negative energy. So that's why that should not happen, because negative energy state doesn't exist here. They are not normalizable. Energy should be greater than 0. That's why this lowering operation this should end somewhere. It should end somewhere. I mean, so there should exist one lowest state here, somewhere here. I call it as psi naught. Lowest state. Again, you will get this psi naught by operating A cap sometimes on psi. Is that okay? You will get into this state. We don't know how many times you have to apply. Okay, we shall see that one. So now this is the lowest state. Corresponding energy, I call it as E naught. I should find both actually. If I apply A minus again on psi naught, I may get into the negative energy. This is the so this is the positive energy. If I again apply A minus on this one, that means that is E naught minus h bar omega. That is the state with E naught minus h bar omega. Am I right? A minus cap into psi naught. If I operate again A minus on this one, you may get into such an energy state whose energy is negative. That is not possible. We should avoid that situation. To avoid that situation, what we write here is, we say this is the lowest state. This is the lowest state. Is that okay? There is no state below this one. If you try to generate a state below this one by operating A minus, you will get into the state of negative energy, which is not normalizable. Again, we shall talk about that hydrogen atom. That's a different story, okay? Their minimum value of the potential, that is negative. It can have negative energy state. Just it's again one-dimensional case. In case of hydrogen atom, your energy is negative, but here energy is positive. Why? Minimum value of the potential is 0. Energy should exceed minimum value of the potential. Otherwise, solutions are not normalizable, not physically acceptable. Is that okay? So that's why I just designed one lowest state. There is no state below this one. If you operate A minus on this one, you will get such a state whose corresponding energy is negative. That is not possible. So that's why if psi naught is the lowest energy state, if psi naught is the lowest possible energy state, if you operate A minus cap on psi naught, I should get 0. That means there should be no state like A minus into psi naught. I'll tell you what happens if A minus into psi naught exists. If A minus cap into psi naught exists, if this exists, then corresponding energy is E naught minus h bar omega, which may be negative. Which is negative. Are you getting my point? I have taken this is the lowest possible energy. There is no possible energy like E minus h bar omega, which is to be negative, which will be negative. That is the idea that I have taken. So that's why I am taking this is the lowest possible state. If you operate A minus cap, if that exists, that would correspond to energy which is negative energy. So that's why if you operate A minus on that one, that A minus into psi naught should not exist. That's what I am saying. You should give 0. Okay? I have taken lowest possible state. Psi naught with energy E naught, lowest possible. Again, whatever I have done, I proved that one. Okay, if you ask the question why I will not get E plus 0.5 h bar omega, again we can't prove like this. He's asking why we can't get like this. Why we can't get E plus 0.5 h bar omega. We can't prove that one. Again, whatever here I have written not by any intuition or something, I have written by a proof here. Is that okay? Yeah. Again, I think you should you should understand what mathematics gives, isn't it? We should follow that one. Lowest possible state, I have taken that one. There should be no state which is lower than this one, isn't it? A minus into psi naught, that would be state with energy E minus h bar omega. And I have taken the idea that E minus h bar omega would be negative. So that's why there should be no that kind of state. That's why I have written this equation. If I operate A minus cap on psi naught, you should get 0. There should be no state which is lower than this one. If that state exists, that would correspond to negative energy. Now, this is nothing but, this becomes one differential equation. Why A minus cap is one operator, am I right? What is this one? 1 by root of 2 h bar m omega, we got? We can find E naught also, we shall see, okay? I p cap plus m omega x cap operating on psi naught equal to 0, am I right? Why this is a differential equation? Because p cap is a differential operator. It's a derivative operator, isn't it? 1 by root of 2 h bar m omega, okay? What is this one? Minus I h bar, am I right? That becomes minus plus dou by dou x, h bar into dou by dou x. Since you have 0 in the right hand side, can I rub out this part? You have 0 in the right hand side. You can take it that side. I into minus I h bar, that means h bar dou psi by dou x, am I right? Operating on psi naught, wait a second, let me write this one. H bar into dou by dou x plus m omega x operating on psi naught equal to 0, that means h bar into dou psi naught by dou x plus m omega x into psi naught is equal to 0. Actually, psi is a function of x alone, time independent solution. Okay, that's why I don't have to write partial derivative, I can write as total derivative. Okay, I mean one dimension. You can write p cap operator like this, minus I h bar d by dx, because in case of one dimension, the function that you are operating on, that will be only one variable function. That's why you don't have to write partial derivative. Partial derivative we use for multivariable function, isn't it? So that's why. So can I write like this? Psi naught is a function of x, variable separable. Now remember, we had no idea what is this state and what is this energy. We restricted that that ladder operation, lowering operation should end somewhere. Otherwise, it may lead to negative energy. And we ended it here. And we are restricting ourselves that there should be no energy lower than this one. Is that okay? We had no idea what was this one. But E naught is positive. E naught is positive. E naught is, again, we should find what is E naught, what is psi naught here. There is no state exist if you operate lowering operator. This means, this statement, this mathematical statement, A minus operating on psi naught equal to 0 means there is no wave function which is lower than this one, or there is no wave function. Again, if it exists, my idea is you may get into negative energy. You should end somewhere, am I right? Again, if you keep on subtracting, you should end it somewhere at negative energy. We should end it somewhere. We ended at psi naught and E naught. That is the idea. Again, you should think over it, okay? You should think little more. Now, if I separate variables, what I can do is d psi naught by dx is equal to minus m omega by h bar into x. You can separate m omega x into psi naught. Okay. You can write d psi naught by psi naught. Psi naught is a function of x, am I right? Variable depend on x like that, okay? That's equal to m omega minus m omega by h bar x into dx. Variables are separated. You can integrate. So that's equal to log of psi naught is equal to minus m omega x square by 2. Am I right? Integral of x dx x square by 2. M omega by 2 h bar x square. Can I write like this? X square by 2. Plus some c, that c I am going to write as log of some c. Log of some constant. So that when I take it here, log of psi naught by c, that's equal to minus m omega by 2 h bar into x square. So psi naught is equal to c into e power minus m omega by 2 h bar into x square. You got your ground state or lowest possible energy state, and you need to normalize to find c. Is that okay? You need to normalize to find c. Now, what is the range of this wave function? That is minus infinity to plus infinity. See the range of potential. Half kx square. What is the range? Minus infinity to plus infinity. So this range of this wave function, again, there is again in particle in a box, it was sine or cos only between 0 to a, or minus a by 2 to plus a by 2. It was 0 outside. This is not like that. You have seen this function. It will go 0 as x tends to plus infinity and minus infinity. Am I right? Normalizable. You got a ground state wave function. Can you just normalize using our integration? Range is minus infinity to plus infinity. Range of interest here in harmonic oscillator, range of interest. Can I say like this? Range of interest. That is minus infinity to plus infinity, not just like in case of particle in a box. Now next idea we should find, just find this one, okay? You will find that C is equal to m omega by pi h bar raised to 1 by 4. You will get this one, okay? You should remember this one actually. You should by heart this ground state wave function because that is needed many times. You can't normalize again, again and again. And even in some CSIR questions, they are expecting you to remember this one, okay? When I see the question, they are expecting you to remember that one. Now, what is E naught? How do you find E naught? Now, operate H cap on this one. I said E naught is the solution again. Psi naught is the solution of Schrodinger equation with energy E naught. I said E naught is the energy corresponding to psi naught. What do you mean by that? E naught is the solution of Schrodinger equation with energy, psi naught is the solution of Schrodinger equation with energy E naught. Now, while applying this one, you got two of these things. Apply it very carefully. Take this one. Why? In this one, A minus is operated first. And if A minus operates on psi naught, you will get 0. Isn't it? If A minus operates on psi naught, you will get 0. If you operate A plus here, it will become higher state. You don't know what is that higher state. So that's why take this off. Again, these two are equal, okay? You can take this one now. If you take that one, h bar omega, A plus cap, A minus cap, plus half psi naught is equal to E naught into psi naught. That means h bar omega, A plus cap, A minus cap into psi naught plus half psi naught. This is equal to E naught into psi naught. Look at here. A plus cap, A minus cap into psi naught means first you should operate A minus, then you should operate A plus. Once you operate A minus, it will become 0. That was our earlier statement. A minus, this is the lowest state, there is no state below that one. Okay. So then this is equal, this part becomes 0. H bar omega plus half again into, this is 0, 0 plus half psi naught is equal to E naught into psi naught. That means E naught is equal to half h bar omega. You got ground state wave function, you got ground state energy. Just check it out. That's a very good question. What they are asking is, look at here, the question is, you have potential, am I right? Half kx square as a function of x, okay? In quantum mechanics, particle doesn't exist if potential is infinity. Particle will not exist at the position where potential is infinity. Now, where this potential is infinity, this potential is infinity at infinity only. Not at any finite position. Isn't it? So, even though you take some energy E here, okay, even though you take some energy E here, look at that one. This is minus x naught, this is plus x naught. You say classically these are two extreme positions, am I right? We call them as classical turning point actually. Now again, this is classically allowed region, this is classically forbidden region. Classically particle will not exist outside this one. But quantum mechanically this wave function, look at here, this if I try to draw this wave function will be like this actually. Gaussian, am I right? We have drawn that one. That wave function exists outside classically allowed region also. There is no restriction like that. Particle can exist outside classically allowed region where classically our kinetic energy would be negative. There is no restriction on wave function beyond classically allowed region. Is that okay? There is no restriction which came. But in particle in a box, potential was infinity outside. Again, our physical restriction itself is particle is trapped, it cannot go outside. That means wave function should be 0 outside. But this is quite different story. We can't say quantum mechanically that particle cannot go outside classically allowed region. It can go actually. Even though there are some two extreme positions, classically, those are classical situation. Particle if oscillating with this energy E particle can exist only between minus x0 to plus x0. It will not exist beyond that one. But there is no restriction on wave function like that. This is normalizable. This is normalizable. Look at the potential range. When potential is infinite, at infinity only. Below that one, potential is finite, isn't it? Particle can exist over there. Possibility. There is a probability. Again, it's not like tunneling. Tunneling is the word used in a different situation. But again, you can say that particle can exist in a non-classical region also, quantum mechanical. That's why you should take minus infinity to plus infinity. That is a possibility. Remember, there is no mathematical restriction on this one. Look at here. After solving Schrodinger, we saw in the case of particle in a box, we solved Schrodinger equation only between 0 to a. And initially we stated that outside that one wave function equal to 0. Because particle cannot enter over there. Here there is no situation like this. Particle cannot enter into this region. That's why you should take minus infinity to plus infinity. That integral exists. It is square integrable. It is normalizable. Its range is minus infinity to plus infinity. Okay. Later we shall study half harmonic oscillator, where our harmonic oscillator is infinity in one. Our potential is infinity in one side. It is harmonic in other side. Then what we take? We take wave function equal to 0 in this side. And we take range from 0 to infinity like that. Is that okay? Again, we restrict ourselves again depending on the potential. Here potential is not restricting it to anywhere. Okay. The range of the potential is minus infinity to plus infinity. Potential goes to infinity only at infinity. That's why particle cannot exist at infinity. But particle can exist anywhere in the real axis. Possibility. Probability of finding the particle may be more here. As you can see, it's a Gaussian wave function. Am I right? It's maximum at x equal to 0. Is that okay? But again, we shall see that one. We shall see much more ideas. Once you got these two, ground state energy and ground state wave function, psi naught of x is equal to m omega by phi h bar raised to 1 by 4 e power minus em omega by 2 h bar x square. And corresponding energy E naught is equal to half h bar omega. Can I write like this? Now this is the lowest state. I called psi naught. Now how do you get higher state? If you operate a plus cap on psi naught, am I right? What would you get? You will get a state with energy E naught plus h bar omega into a plus cap psi naught. Isn't it? Like this, if you keep on operating, look at here. Again, if you operate a plus cap twice on this one, what will you get? E naught plus 2 h bar omega. A plus cap square into psi naught. Like this, if you operate a plus cap n times on psi naught, you will get into the state E naught plus n h bar omega a plus n times psi naught. Okay. What is this E naught? Can I keep on writing that one? Half h bar omega. Half h bar omega. Half h bar omega. Isn't it? Now I call this one as nth state. I call this one as nth state. I call this one as zeroth state. Zeroth. Not zero, zeroth state. Okay. I call this one as nth state. Okay. I write that nth state as psi n is equal to, I should put some constant because we don't know after operation of this one, this was normalized, isn't it? Once you operate a plus, we don't know what would happen. So again, after operation, it need not be normalized, isn't it? That's why I put one normalization constant. I call that one as an. An A plus cap operated n times on psi naught. Is that okay? A plus cap operated n times on psi naught. Wait a second, let me comment on that one, okay? Just put it into Slack. What he's saying is quantum mechanical oscillator, can it have negative kinetic energy? No, actually, okay? I mean, you can't interpret negative kinetic energy possibility. Yeah, wait a second, let me try to explain, okay? Yeah. Is that over? You will get nth state like this, psi n of x. Psi n of x is equal to and corresponding energy, I call that one as nth energy. Corresponding energy, I write that one as En. This one I'm going to write as En. I'll just manipulate and write this one. I'll write it as, so n plus half h bar omega. N plus half h bar omega is taken outside. Is that okay? Just I'm manipulating. So we can generate nth state using the ground state. We already found ground state. If we, and we know what is that operator, we can find nth state. We can find nth energy. Now I can just write n is equal to 0, 1, 2 and so on. Am I right? N can start from 0. If n equal to 0, you will get E0, psi 0. A plus cap operating 0 times psi naught means leaving it as it is. If you put n equal to 0, that means that's equal to psi n equal to psi naught. You will get psi naught. So this is the most general statement. You got nth wave function in terms of ground state actually, not directly, but you got nth energy value, look at here. Without solving differential equation, we got this much result. And solve example number 2.4. Do example number 2.4. Finding first excited state by operating A plus cap on psi naught, okay? Just try to do that one. Now look at here. In quantum harmonic oscillator, you can't mute energy. If you put n is equal to 0, what is the lowest energy? Half h bar omega. But classically, we can keep it at 0 energy. Is that okay? And in case of quantum harmonic oscillator, when you see the wave function, which extends outside classically allowed region also, which gives probability of finding the particle over there, okay? If particle exists over there, again, it doesn't mean particle will be moving over there, okay? So he's asking that if particle exists outside classically allowed region, its kinetic energy will be observed to be negative, am I right? We can't interpret that one actually, but if particle exists over there, you will not feel the particle which is in moving or something. Is that okay? That is, once you find the particle, it will show off one of the position. You can't judge what is its momentum then. Kinetic energy is related to momentum, isn't it? Isn't it? To talk about kinetic energy, you should know the momentum. Once you do the position measurement, again, it will not show off any other result. You will find one of the position. You can only say particle can exist outside classically allowed region. There is a finite probability of finding the particle. You can't say anything about its momentum or kinetic energy. Again, uncertainty will not allow us to talk about both of those variables simultaneously. We can't talk about both of the variables simultaneously, okay? Again, there are some other problems also like this. So try to interpret like this, okay? That's a very good question. And keep that question in Slack, okay? If I get any other idea, I'll try to interpret it in some other way, okay?